Let's begin with a simple example. Imagine a clean and perfectly organized bedroom. As time passes, the room is used, the bed becomes unmade, clothes are left around, trash begins to accumulate, and eventually the room needs to be cleaned. But why? Why does disorder seem to appear naturally as time goes on? And this is not the only example. Ice melts, perfume spreads throughout a room, a drop of ink disperses in water. All of these phenomena seem to suggest that physical systems naturally evolve toward more disordered configurations. But is that really what is happening? This is where entropy enters the picture, one of the most fascinating and also one of the most misunderstood concepts in physics. Today, we will discover what entropy really is and how one of the most important laws of thermodynamics explains these everyday phenomena. Before we continue, we need to clarify one fundamental point. Very often people say that entropy is the measure of disorder in a system. Although this definition is widely used, it is not actually correct. It is true that entropy and disorder are closely related, but not by definition. Rather, disorder is a consequence of what entropy really measures. To understand what entropy truly represents, let us consider a simple example. Imagine a box containing a few particles. There are many different ways in which these particles can be arranged inside the box. It is much more likely to find them distributed in an apparently random way than perfectly aligned in an ordered configuration. And this is the key idea. Entropy measures how many microscopic states are compatible with the same macroscopic state. In our example, we represented the particles as simple spheres to make the concept easier to visualize. In reality, they could be atoms, molecules, or any other microscopic particles. Each possible arrangement of these particles is called a microstate. The observable properties of the system instead define its macrostate. Entropy therefore measures how many different microstates can produce the same macrostate. Mathematically, this idea is expressed by the famous Boltzmann equation, S equals K times the natural logarithm of omega, where S is the entropy, K is the Boltzmann constant, and omega is the number of microstates associated with a given macrostate. The greater the number of possible microstates, the greater the entropy of the system. Now notice something interesting. The equation never mentions disorder. It only counts the number of microscopic configurations. So entropy is not a measure of disorder. It is a measure of how many microscopic configurations are possible. Once we understand this, the phenomenon becomes a matter of statistics. If one macrostate can be produced by an enormous number of microstates, it is far more likely to occur than another macrostate associated with only a few microstates. Nature does not follow a predetermined plan, and it does not actively move toward disorder. Instead, physical systems tend to evolve toward the macrostates that can be realized in the greatest number of microscopic ways, and these macrostates are usually the ones that appear more disordered to us. This is why disorder is a consequence of entropy rather than its definition. Another classic example is a falling glass. Imagine dropping a glass onto the floor. After the impact, it breaks, and its fragments scatter in many different directions. Could those fragments move in exactly the right way to reconstruct the original glass as though it had never fallen? In principle, the answer is yes. The fundamental laws of physics do not absolutely forbid it. But this would require every fragment, every molecule, and all the energy dispersed as sound and heat to move in an extraordinarily precise and coordinated way. The number of microscopic conditions required would be incredibly specific. It is therefore overwhelmingly more probable for the glass simply to break and remain broken. This tendency toward macrostates with more available microstates is expressed by the second law of thermodynamics. For an isolated system, delta S is greater than or equal to 0. An isolated system exchanges neither matter nor energy with its surroundings. Its entropy therefore tends to increase over time, or at most remain constant. In other words, the system tends to evolve toward macrostates that are compatible with a greater number of microscopic configurations. Small fluctuations toward lower entropy can occur, especially in very small systems. But for macroscopic systems, a significant decrease in entropy is so improbable that we practically never observe it. Just as with the broken glass, Decreasing entropy would require the system to move spontaneously from an overwhelmingly probable macrostate toward an extraordinarily rare one. Let us consider one more example, still within thermodynamics. Suppose that two bodies at different temperatures are placed in thermal contact. They begin to exchange energy in the form of heat until they eventually reach thermal equilibrium. More precisely, the net flow of heat moves from the hotter body toward the colder one. But why does the opposite not normally happen? Why does the colder body not transfer a net amount of heat to the hotter one, making the temperature difference even greater? Once again, the reason is statistical. When energy is concentrated unevenly between the two bodies, the system is compatible with fewer microscopic configurations. When that energy becomes more evenly distributed, there are enormously more possible microstates. For this reason, the system naturally evolves toward thermal equilibrium. This does not mean that individual particles transfer energy in only one direction. Microscopic exchanges occur in both directions, but the overwhelmingly most probable overall result is a net transfer of energy from the hotter body to the colder one. Through this and the previous examples, we can understand that many physical phenomena can be interpreted through entropy. More precisely, systems tend to evolve toward macrostates compatible with a greater number of microstates. But, as we have already said, this does not mean that everything must become chaotic. Plants grow and develop highly organized structures. Living organisms maintain complex and functional internal organization. This is possible because they are not isolated systems. They exchange matter and energy with their surroundings, and they can reduce their local entropy while producing a greater increase in entropy in the environment. This because the second law applies only to closed systems, not open ones like the last two examples. Finally, we can answer the question we asked at the beginning of this video. Does the universe love disorder? The answer is no. The universe does not move toward disorder. It moves toward the most probable macrostates, the ones associated with the greatest number of possible microstates. Very often, these macrostates simply appear more disordered to us. And once again, this is a relationship of cause and effect, not a definition. That is what entropy really is. One of the most fascinating and most misunderstood concepts in physics. If you enjoyed this video, consider subscribing to the channel and leaving a like. Thank you for watching, and I will see you in the next video.